Welcome to Chapter 7 lecture. This is going to be 3 parts as usual, Part A, Part B, and Part C. Make sure you watch all the parts before you take Chapter 7 quiz. In Part A, we will cover section 7.1 through 7.4. Part P 7.5 through 7.7 and Part C 7.8 through 7.10. Please get ready with your notebook. I will be solving some examples which you will need to refer when solving either suggested at end of the chapter problems or when you will be completing the Module 7 in Alex. So let's get started. What is thermochemistry and why do we, what is the significance, what's the relevance? Why do we have to study thermochemistry? You need to understand the term first, and then why do we have to learn thermochemistry? As usual, I'll have my whiteboard and PowerPoint slides. This is the chapter outline. As I said, I'll split the chapter into 3, Part A 7.1 through 7.4, 7.5 through 7.7. We look at Part B, Part C 7.8 through 7.10. Let's get started with the definition first of what is thermochemistry. How do you define thermochemistry? In simple terms, thermochemistry is the study between or relationship between chemistry and energy. Recall in chapter 1, at the beginning of the semester, we defined the word chemistry as the study of matter and its transformation. And there is something new we will focus or we will look in details in chapter 7, the energy, all right? Some others define thermochemistry as the relationship between chemical reactions and the energy. In Intro to Chemistry, probably you define 2 terms, which we will also look at in chapter 7. This is exothermic, chemical reaction which gives away heat, or endothermic, which absorb heat from the surrounding heat. In this case, is the heat energy being released or absorbed during chemical reaction. The study of the relationship between the two is simply what thermochemistry is. And why do chemists study thermochemistry? There are a lot of reasons as to why, but I'm just going to give you 3 reasons why, or the importance of thermochemistry. One, it helps in determining whether a chemical reaction will occur or not, and if yes, will it release heat or will it absorb heat during the process? It makes no sense to, maybe waste your time, waste a chemical reagent in the long run to figure it out that, the reaction will not proceed as desired. So thermochemistry helps you or help chemists to figure it out before they perform an experiment or before they carry out any reaction. Thermodynamics will help in predicting whether the reaction will proceed. Apart from that, you can also predict the products of a chemical reagent, predict the reagent in a chemical reaction, and lastly, even in energy production, okay? We use thermochemistry. I just want to highlight that these 3 points here, these are not the only reason why we study thermochemistry. There are other reasons. For example, right now, summertime, we need to cool our homes. Thermochemist has to be involved in there. During winter time, we need to warm our homes. There's thermochemistry in there. We will look at it in details or a little bit in 7.1 on the chemical hand warmers. Some of you may have used the hand warmers before. If not, it's not a big deal. We will look at the thermite reaction and the process by which heat is released in thermite reaction. In 7.2, we will look at the few definitions you need to bear in mind. I will ask you probably in the quiz or in the upcoming exam some key definition you need to understand. What is thermodynamics? What is chemistry? What is energy? What is work, and so forth. In 7.3, we will look at the first law of thermodynamics, which I know some of you know how to define. It's just energy conservation, which states that energy cannot be created or destroyed. It's only transformed or transferred. Energy cannot be created or destroyed is the first law of thermodynamics. There are three laws you will cover in Chem 2 for those who will proceed to Chem 2. Two other laws which I don't want to delve into at this time. 7.4, chemical reaction can either transfer heat or energy in form of heat or energy in form of work. Remember, we talked about relationship between chemical reaction and energy, right? The energy can be transferred in form of heat energy or in form of work. We will look at in 7.4, quantifying the heat transferred and the work either done by the system or done on the system. So introduction, let's look at the nature of chemical energy. Okay. Recall in chapter 1, we define energy as the ability to do work or transfer heat. We need to define that. In this chapter, it's about thermodynamics. There is a whole chapter in Chem 2 on thermodynamics, but for now, it's just define thermodynamic, which is the study of energy and its transformation. Remember, energy cannot be created or what? Or destroyed, but it can be transformed. For example, the chemical energy stored in gasoline, the chemical bonds in gasoline has some energy, which can be transformed into other energy. For example, when the chemical bonds are broken, energy is given off, which can be transformed into light energy in your car, or sound energy for your stereo, or heat energy if you are warming your car, mechanical energy in the engine to move the car, and so forth. All right, even sound energy from the stereo. All those are form of energy transformation. Thermochemistry is a branch of thermodynamics. I want to highlight that. You need to remember that thermochemistry is a branch of thermodynamics, which is the study of energy and its transformation. And I just define this. You need to be able to define thermodynamics and thermochemistry. So this is the umbrella, and thermochemistry is a branch of thermodynamics, which is the study of chemical reaction and the energy involved. It can be either heat being absorbed or heat being released. Now, you may have used or you may have heard about chemical hand warmers. It's just used to warm the hands, like especially up north during winter, or maybe people hiking up in the mountain with freezing temperatures. To keep their hands warm, they use what we call hand warmers. And what takes place in there is what we call thermite reaction. Let me just write that. This is called, you see in the text, reaction. And if you look on the chemical equation, it is iron in solid form reacting with oxygen gas to form iron. This is iron 3 oxide is solid. There is heat here, by the way, heat, and this is X exothermic. Sorry to preempt this, but we will look at it in details later on. Exothermic and endothermic heat is given up. This is what is responsible for warming the hands. This is exothermic reaction, some reaction. You see the importance now of studying thermochemistry, right? Because how did they end up knowing that this chemical reaction will release heat? Is by taking advantage of thermochemistry, which they can predict the product. And one of the product here is heat being released. Read more on our chemical hand warmers on section 7.1 in the text. All right, the reaction is exothermic. Exothermic, let's get started with learning some of the new terms here. Release heat to the surrounding and thermic reaction, absorb heat. All right. So if I go back here, if this is the reagent A plus B going to C, for exothermic, we will have heat on the product side. For endothermic, it's going to be heat, all right, plus A plus B going to C. So this is the reagent, or heat is on the reactant side, whereas on exothermic, it is on the product side. That's the difference between exothermic and endothermic. And this reaction, thermite reaction, is exothermic. It keeps away heat, which is responsible for keeping your hands warm. The amount of your hand temperature rises depends on the several factors. For example, the size of the hand warmer. If it's small, then of course small amount of it will be released. The size of the clubs, of course, surface area will also affect the amount of it given off, right? Given off. Now let's see. Heat definition, section 7.2. You need to commit this to your memory. All right. Even though chemistry is the study of matter and its transformation, energy also affect matter. Energy affect matter. For example, of course, if you increase the temperature, an ice cube will melt. That means it will affect what? It will affect its physical state. If you increase the temperature of any substance beyond its vaporization point, it will change from one state to another. So we know the energy affect also matter. We have defined this. I know you can define thermochemistry, but now energy is defined as the ability or the capacity to do work. We define this in chapter 1, but still we are revisiting the term energy, which is the ability or capacity to do work. Then work is force acting over distance. Work is force times distance. Work is force. Whereas heat is the flow of energy caused by difference in temperature. Okay. Quite often, students do confuse between the heat and temperature. Heat is the flow of energy, whereas temperature is the average kinetic energy of a particle of a substance. So when we talk about the temperature today being at high 90s, we are talking about the average kinetic energy of air particles. Likewise, for any other substance, such as H2O, we are talking about boiling point for water, literature value being 100 degrees Celsius. We are talking about the average kinetic energy of particles, which is the temperature, not the heat, which here we define as the flow of energy caused by difference in temperature. You cannot interchange the word energy, I mean the heat and temperature. Use temperature to define the heat. Energy can be exchanged between objects through contact, for example, through collision and so forth, which energy can be transformed, can be changed. You can think of energy as a quantity of object can possess, an object can possess as a collection, but heat and work as two different ways that object can exchange energy with other objects. So these two terms can be a way an object can exchange the energy with other objects, which can either be in or it can either be going out, can either be doing work or work is being done. There are several types of energy, all right? There is the potential energy, kinetic energy, which is the energy in motion. Energy possessed by moving object is called kinetic energy. You will see the abbreviation KE, you may have seen before, or PE for potential energy. This is the stored energy or the energy by virtue of position. I have my watch here. I don't know if you can see, probably because of the background, you may not see that. But if I have an object here and then I release, it will fall down by virtue that I've raised it by virtue of position or composition. Water at the top of the mountain has potential energy. If we release the water, it will just flow down the hill because of the potential energy. If you raise an object, it will have potential energy by virtue of position. By virtue of composition, gasoline, I used gasoline before, has stored energy by virtue of chemicals stored in it. Coal, for example, has a stored energy. The food we consume has energy. We'll need energy to do activities for working, talking and so forth. Those are stored energy. You can think of other forms of potential energy. Thermal energy is the energy associated with the temperature, all right? Thermal energy is a form of kinetic energy. Here is just the illustration of how kinetic energy is transferred from an object to another object. Here is a ball, stationary. There is a white ball here, possessing kinetic energy. It will transfer its energy to the stationary ball, and the stationary ball will start moving because of energy being transferred. Kinetic energy or simply energy can be transferred. This is kinetic energy. Energy possessed by moving object. Please memorize the few terms I've given you: kinetic energy, potential energy, thermal energy, chemical energy, and so forth. Let's see, potential energy is the energy that is stored in object or associated with the composition or position of an object. For example, a raised ball has potential energy by virtue of its composition. When it's released, the stored energy will be transferred into kinetic energy. It will gain energy as a result of gravitational force acting on it. So potential energy is transferred to kinetic energy. Chemical energy, these are the energy, potential energy due to structure of atoms. The attachment, the chemical bonds, position relative to each other in a molecule. This is a form of chemical energy which can be transformed into other form of energy when an atom or when a molecule or a compound react with other compound in a chemical reaction. As I said, we're looking the law in the first law of thermodynamics, which is basically the conservation of energy, which states that energy cannot be created or destroyed. This is the law of conservation of energy. We'll see later on that it's also called the law of first law of thermodynamics. Here is how the conservation of energy is illustrated when energy is transferred from object or converted from one another. The total amount of energy present at the beginning will be present at the end. No loss of energy. No loss of energy. So up to this point, I will highly recommend that you make your own notes or commit those terms to your memory, the definitions we looked at, and the types of energy. You should be able to cite examples and define or draw a parallel between the two types of energies we covered. Now, there are two terms here I want us to understand as we move on in chapter 7, system and surroundings. Systems and surrounding. What is a system? You know, system, when we say a system, we may think that it's the other system you may think of, or when we say surrounding, you may think the surrounding where you are sitting right now, but let's focus on what chemists actually mean when they say the system and the surrounding. If this is our reaction flask, this is a flask. I'm just gonna write here. This is Allen Meyer flask. When you're familiar from the lab, let's say we have reagent A reacting with P to form the C. What is in the flask is the system. We call this system. This is what? This is where we focus. Whereas here, everywhere, what surrounds that is called the surrounding. For example, in the lab, if you are mixing the reagent in a flask, that is your system. But outside in the laboratory, that is the surrounding. That is the surrounding. Chemists use this to define the system plus surrounding equals to what we call the universe. So that's what we call the system, the surrounding. I can illustrate that again using this diagram, that if this is our system, A plus B equal to C, this is the system. And then here, this is the surrounding. And then everything here, including the system, is the universe. You see, system plus surrounding equals to the universe. Is equals to the universe, not the universe the way we know where we live, including the planets, including the stars. The universe is the system plus the surrounding, and then the surrounding is what we focus on. So there are different types of system. We look at it momentarily, but we define the system as the material or process within which we are studying the energy changes. All right, energy changes, which can be, if we talk about exothermic, that means it's gonna give away heat. all right, or endothermic, which can mean coming in. This is the area where we focus, we look at the energy, say, is it releasing heat or absorbing heat from the surrounding? We define the surrounding as everything else with which the system can exchange energy. Look at how I have illustrated the surrounding. Outside the system is the surrounding, and it can be released to the surrounding by the system, or the system can absorb heat from the surrounding. Remember, you don't say surrounding release heat to the system. Is the system absorbing heat or releasing heat? This is where you need to conceptualize and say you are in the system, and if the heat is released or absorbed from the surrounding. We studied the exchange of heat energy between the system and the surrounding. So here, this is the energy. It can be absorbed, all right? Energy can be released as well. Energy can be released. We have defined the system, the surrounding, and here is the universe. I was just explaining what it means. The portion of the universe is everything is the universe, and the system is the portion of the universe we single out to study. That is where the reaction is taking place. There was an illustration of oxygen gas reacting with hydrogen gas to form water molecule, all right? This will be our system. This will be considered as the system in that reaction. Everywhere else will be the surrounding. Here is the diagram illustrating the reaction between oxygen and hydrogen. This the surrounding outside, excluding the system. Now, there are three types of system you need to understand. There is the open system, where there is exchange of heat and mass. So heat is lost by the system as well as the mass. So there are two things you need to remember, which we use in defining the type or classifying the system. Is it either losing both heat energy and mass? Heat and what? And mass. If it is losing both, we talk about open system. Heat can escape, mass can escape as well. There is the closed system, all right, closed system, which means only heat can be lost, but not the, it cannot include the mass in closed system, For example, if you put hot water in a closed container, heat will be lost, but not the mass. If you hold it, you'll feel it's warm or it's hot. That means heat is being released, but not the mass, because there is a lid closed on it. Now, our example of closed system is cup of tea in a container with a lid, all right? Even the earth where we live is a closed system. Here, example of open system include human body. Our bodies, we can lose heat, we can lose mass as well. Automobile engine also can lose heat, can lose mass as well. A beaker of water is an example of open system. And then there is the isolated system, all right, where neither mass or heat can be lost. Example of this include the pump calorimeter, combustion in the pump calorimeter. We'll see down the line where combustible material is burned in enclosed chamber. In this case, we call calorimeter. Neither heat or mass will be lost under circumstance we talk about isolated system. So there are three types of system you need to understand so that when you are given a specific system, you should be able to classify as either open, closed, or isolated Here is a good example on testing yourself if you have really mastered the three terms: closed, isolated, or open. Is human being an isolated, closed, or open system? I gave you as an example. In essence of time, human being is an example of open system. We can lose both mass as well as heat. So it's going to be open. It can be isolated, it cannot be closed system, but it's C, open system. Now, with respect to heat energy being released by the system to the surrounding, remember the law of conservation of energy. Energy can neither be created or destroyed. So conservation of energy means that the amount of energy gained or lost by the system has to be equal to the amount lost or gained by the surrounding. Here is an illustration of the bullet point here. If this is the system and this is the surrounding, if this is a ruler, right? If I look at the ruler here, before the transfer, put 1, 2, 3, let's talk about like 3 centimeters, 1 centimeter, 2 centimeter, 3 centimeter. It's the same thing here. If I look at, if I transfer 1 centimeter, it's just gonna be half. So here, if we transfer 1, this will be 2. So the total energy of the universe is the same. Whatever the system loses, the surrounding gain equal amount. Energy cannot be destroyed, but it can be transferred. Here, 1 centimeter has been transferred by the system to the surrounding, and we end up with 2 centimeters of the surrounding. I'm just using the word centimeter because of the calibration of this diagram. We are left with 1 centimeter from 2 centimeters here, just to understand the conservation of energy. Conservation of energy be transferred. Now, there are different units of expressing energy. You should be able to convert energy from one unit to the other units using dimensional analysis. Dimensional analysis we learned earlier on. Given an equivalent statement, you should be able to generate conversion factors so that you reconcile the units, then you get your desired unit for the energy. Recall kinetic energy, energy in motion. This is the equation for calculating energy. And remember, for mass, all right, mass has to be in kilogram. Mass has to be in kilogram. For kinetic energy equals to half mv squared, where m is mass in kg and v is velocity or speed in meters per second. You need to change. If the speed is in kilometers per hour, miles per hour, or any other units, you need to change to meters per second, change the mass to kilogram, because if we have this, we'll have to relate the units of energy. And it turns out that 1 joule, which is the SI unit, all right, J joules here, J, this is the System International SI unit for expressing energy, SI unit for energy. And 1 joule, please take note of this. We'll use again, 1 joule is kilogram times meter square over second square. Or simply, this is the same thing, meter square over second square. Meter square over second square is the same thing. So that we can now convert. Once we have that, we convert into joules, which is the SI unit for expressing energy. There are other units of energy, calorie, which is 4.184. And I want you to take note of the difference between calorie with uppercase C and calorie with a lowercase c. 1 calorie, please, which is used by nutritionists, 1 uppercase calorie equals to 1,000 lowercase calorie. See this? So that you can convert that. And then 1 lowercase calorie equals to 4.184 joules. So you need to be able to convert the units of energy or measurement in energy from one unit to another unit, given any of these equivalent statement. I will give you an exam if need be. I'll give you in the quiz if need be, if you need to convert energy from one form to another, or from one unit to the other. Now, for module 7, Alex assignment, you may need to refer to the text. You may need to refer to the PowerPoint slide here before you convert the energy to another form. Here is an example on energy conversion. We need to convert 567 calories to joules, and we have 3 significant figures, so one significant. Recall here, this is what you need to remember. 1 calorie equals to 1,000 calories, lowercase calorie. And then 1 lowercase calorie equals to 4.184 joules. But you need to remember that. So we need to convert the calorie, the big one. So you set up your equation, 567 uppercase calorie. I want to get rid of uppercase calorie like that. And then I'll end up with lowercase calories. I need 1,000 here for everyone. This was given in the previous slide. Times now, we want to change the joules. 1 lowercase calorie equals to 4.184 joules. So that when we reconcile the units, this will go, that will go, that will go. And what will remain with is you see on your calculator 232.8 joules. This is more than what we need in significant figures. This is 3 here. So expressed with the correct number of significant figures in scientific notation, this will be 2.37 times 10 raised to 6 joules. All right, joules like that. That is the answer expressed in 3 significant figures. These conversion factors you need to generate. As I said, you will be given, if need be, But if not, you need to refer to the right page. 1 lowercase calorie equals 4.184 joules. That's where I got this number here. And 1 calorie used by nutrition used uppercase is equals to 1,000 calories. That's what I use for the second conversion factor. And I had to start with this because I wanted to get rid of what I'm given in the problem here. This is what we are given to convert. Please refer to problem 33, 34, 35, 36, 37 on page 306, 307 in the text practice on converting energy in 1 unit or from 1 unit to the other unit. These are other use of energy. If need be, you'll be given those, but refer that just for your own general understanding. Moving on, section 7.3, the first law of thermodynamics. It's just the law of energy conservation, which says that energy cannot be created or destroyed, but it can be converted from one form to the other form, which I said before. It falls under the chapter on thermodynamics, which is the study of energy and its interconversion. If we cannot create energy, if we cannot destroy energy, we can just transform from one form to the other form. For example, the nuclear energy in the sun, all right, is transformed into the light energy we used to see things, light energy or heat energy when you go out there to, to get the sunlight, or, is transformed from the nuclear energy from the sun to light energy to heat energy and so forth. Those are in the conversion, Even nuclear energy from the nuclear reactors to generate electricity, and from electrical energy, we can transform to light energy, to heat energy, to mechanical energy, and so forth. All those fall under thermodynamics. The first law of thermodynamics states that energy cannot be destroyed or created. You should be able to state that. This means the total energy in the universe is constant. It will never change. It will never change. Therefore, you can either design a system that will continue. You can never design a system that continues to produce energy without some of it being lost. So be able to define that. First law of thermodynamics. So to heat our homes, we need chemical energy, which is converted to heat energy in warming our home or even cooling it down. Sunlight is converted to chemical energy in green plant during the photosynthesis. There are many other examples of conservation of energy. I know you can also list the form of energy transformation, other forms of energy transformation. Our bodies as well can convert the chemical energy in the food we consume into mechanical energy for us to move around, okay? We can move unless we eat. We need food, and the food we consume has stored energy, chemical energy, which is converted into mechanical energy. We use this diagram before to illustrate the transformation of energy from the system to the surrounding. There is this symbol here means change. Change in energy equals to 0. There is no change of energy in the universe. When I say universe, remember the diagram where I had a circle representing the system, and the surrounding, and everything the surrounding plus the system. This is what is meant by the universe. Don't think of the universe we have. Remember, system plus surrounding, I gave you earlier on. System plus surrounding equals to the universe. That's what is meant by here. And the symbol here means change. You will see more and more the use of this symbol. Delta, it means change. So change in energy in the universe is zero. There is no loss because of what we just said about the conservation of energy, or the first law of thermodynamics. There is a new term here you need to understand. E stands for internal energy. I don't know why internal energy, we do not use I as the symbol for that, but we use E, which I think probably you may say energy for E, but strictly speaking, in thermodynamic, E stands for internal energy of the system, which is the sum of kinetic energy and potential energy. So change in internal energy, or E, which is internal energy, is the sum of kinetic energy plus potential energy, where this is internal. This is internal energy. We talk about internal energy of the system, internal energy of the system, sum of potential and kinetic. State function, let's define this term here. What do we mean by state function? It does not mean something which happens or which takes place in Tallahassee, that is the capital of Florida. I'm in Florida right now. UNF is in Florida, and I'm using Tallahassee, which is the capital of state of Florida. So when we say state function, does not mean that the state is organizing that function. In thermodynamics, we should be able to understand what is a state function. A state function is a mathematical function whose results depend only on the initial and the final condition, not on the process. For example, altitude. In the next slide, you will see how altitude is a state function. It does not depend on how we got there. Temperature, for example, to give you examples of state function, temperature is a state function. It does not matter what the temperature last week, that is going to affect the temperature right now. Or the temperature in the morning will not be the same as the temperature at night. It does not really matter how we get there, all those are state function. Change in internal energy, final minus initial. So for change in internal energy for the reactants, for reactions, product minus reagent. This means the internal energy of the products minus internal energy of the reagent. So for state function, let's see. What do we mean by state function? Here is an illustration for you to understand what a state function is. Altitude, the top of the hill, top of the mountain, you may call it, from the sea level to the highest point of the mountains is 1,000 feet, 10,000 feet above sea level. This is the sea level. The highest point of this mountain is 10,000. To get to this height, this altitude, it doesn't really matter if someone is meandering. You see how this path is just meandering? It's take like 12 miles, but you don't get tired if you walk through this road because it's just like going through. And let's say person B or person A. Person A is going through this road. At the end of it, it's 12 miles. This is just like boom, straight. Top of the hill. At the top, both of them will be at 10,000 feet above sea level. And it doesn't really matter which path you take in there, we say it's a state function. The distance from the base of to the peak of the mountains is a state function. It only depends on the difference in elevation. Final minus initial altitude, final minus initial is 10,000. But how we got there, it doesn't really matter. We can either take the long route or the short route, regardless of the trial or trail. When you reach the top of the mountain, you will be 10,000 above sea level. This is just an illustration. There will be some thermodynamic terms as we cover thermochemistry. We will be saying, oh, this is a what? This is a state function. For example, the internal energy, which is the sum of potential energy and kinetic energy, is a state function. Is a state function. Okay, state function. It's a property of the system that is determined by specifying the system condition at that particular time, not before or not after. And remember what we mean by the system. I want you to understand the system with respect to the surrounding and the universe Usually, we have no way of knowing the internal energy of the system. Finding the value is simply too complex. We're not going to get in there. Here is an illustration of water, 50 grams of H2O at 25 degrees. How we end up with this condition right here? Remember, we say we specify the condition. How we end up right here, right? We can either cool water at 100 degrees Celsius, 325, or we can melt ice at 0 degrees Celsius, raise the temperature to 25. It doesn't really matter how we get there. So temperature is a state function. Doesn't really matter how you get there. Okay. We talk about that. Therefore, the internal energy is the state function. It only depends on the presence of the system, not the path by which we arrive at that time. So change in the internal energy depends on the initial and the final. This is what we talked about here. All right, that's what we talked about right here. So far, we have defined what internal energy is, the symbol we use for internal energy, symbol for use in change in internal energy. Now, the flow of energy in a chemical reaction. Remember, the reaction is our system. Is energy flowing out of the system, or energy is flowing from the surrounding to the system? The author here uses 1 mole of carbon reacting with oxygen. These are the reagents to form carbon dioxide. If the internal energy of the product is lower than the internal energy of the reagent, change in internal energy will be negative, which means it's giving up. Remember that? The reaction is giving away heat. Negative means change in losing, while the surrounding is gaining. We'll see that as well for reaction of CO2 here. See product. In other words, the internal energy of the system is higher than the internal energy for the reagents. We have flipped the equation now. In the previous section, we were forming carbon dioxide from the element carbon and oxygen. But if we flip the equation, stands out that the internal energy of the product is higher than the internal energy for the reagent, and we say final minus initial, we'll end up with a positive change in internal energy, So either energy flows out of the system to the surrounding. See the system, this is the surrounding. For the system, change in internal energy for the system is negative, whereas for the surrounding, it is positive. There is a relationship between the internal energy for the surroundings positive, whereas that is gaining. Now, for the system gaining, you see, surrounding the energy flow from the surrounding into the system, which means the system is gaining, which will result in positive change in internal. Remember, in number line, anything greater than 0 is positive, whereas the surrounding will have a negative change in internal energy. The point here is from the previous slide, and this one is what is the sign of change in internal energy for the system compared to the surrounding. If the surrounding is losing, it means the system is gaining. System is gaining. Gonna have that later on. It's the same thing representing the change in internal energy graphical, same as the one we looked at. This means if the reagents or reactant have higher internal energy, this is the reagent, it will be negative. Whereas it's the opposite. If the reagents have less, all right, if the reactant have lower internal energy, then the energy of the product, the change in energy will be positive for the system. When we say positive, it is with respect to the system where we need to focus on. So this is in summary. If the reactant have higher internal energy than the product, the negative, then change in internal energy for the system is negative, and the flow energy flows out of the system into the surrounding. Please take note of that. Whereas if the reagent have lower internal energy than the product, then change in internal energy for the system will be positive, and the flow energy flows into the system from the surrounding. That's just the flow of the energy. Is it carrying out? And then if it's carrying out, what is the sign of change in internal energy for the surrounding and for the system for the two scenarios we have in there. So here is the change in, look, consider the fictitious internal energy causes. You see this? This is a learning check. Consider these fictitious internal energy cages that describe the initial condition for a chemical system and its surrounding. If I look at using the centimeter analogy, 1 centimeter, 2 centimeter, 3 centimeter, for the chemical system and the surrounding, if we transfer everything from the surrounding into the system will have a full scale, all 9 yards. We take this. So which energy cages corresponds to final condition following an energy exchange in which change in internal energy for the system is negative. That means the system is losing and the surrounding is gaining. So if it is losing, that means this will be less. So if I look at C is wrong, this cannot be the case. If I look at this, the most appropriate is A, because if the system is losing, that means negative. You need to understand the sign convention for change in internal energy, that if the system, this will reduce, and if we take 1 centimeter here, it's going to be the same. So appropriate here is A. This kind of question is conception. I don't want to give you calculation in the quiz that everything is mass based. No, sometimes I give you definition. Sometimes you may have the conception. You just have to look at it. And this slide here is just nothing but understanding the sign of change in internal energy for the system and for the surrounding. You can make your own notes by reading the relevant section in the lab manual. So for this, the correct answer is A. The correct answer is A. Now, let's move on to looking at the 3 parts of thermodynamic quantities. It has a number, it has a unit, and it has a sign. Remember what we were talking about, the sign, negative, positive, you need what it understand. As usual, you know, in chemistry or in science in general, a number has to have a unit, otherwise it will just be a meaningless to it. We just looked at the conversion of energy from different units, either in calories or either in joules. So we must have a unit attached to it. Note about the sign, positive change in internal energy result when the system gains, positive gains, all right? Think of exothermic, endothermic. Negative change in internal energy means it loses, and this means the system. Remember how I defined the system earlier on? The system is where we are focusing on, where we are looking at. So it's either carrying out, that means the system is gaining, which is positive, or the system is losing, which is negative to the surrounding. We have looked at internal energy. Let's look at how the system exchange energy. It can either be in form of work, or it can either be in form of heat energy. Moving on, heat will be represented by Q, means heat, and W will be, or will represent the work. And when we talk about that, either the system is losing energy in form of heat or in form of work, whichever way it is. And for the sign convention, you have to be in the system for you to understand. Therefore, if this is our system, all right, this is the internal energy. Look at the black parts. Either heat is coming in, and anything greater than 0 is positive. That means positive. Anything carrying out is negative. So work done on the system. Work done by the system. It is carrying out. Again, don't ignore this notation right here. Anything greater than 0 is positive. So that means it's getting into the system. Anything heat is lost. Anything less than 0 is negative. That means it's getting out. Anything less than 0 is negative. That means it is getting out of the system. This notation is greater than or less than. Please recall from the number line. This is probably something you learned earlier on in math class. So you have a number line right here. Let's say this is 0, this is -1, this is -2, this is -3, this is 1, 2, 3. So anything greater than 0 is positive. Anything less than 0 is negative. Anything less than 0. So there will be sign convention for this as well, which you need to know. It will affect how you calculate the total internal energy. If you don't know the sign convention for this, especially when we say the work is done by the system or the system is doing work on the surrounding, it will affect how you calculate the internal energy. Remember, this is the equation you need to remember. I will give you this one, means change in internal energy is the work plus Q, and this can be negative, this can be positive, this can be negative, this can be positive. Please learn this convention. Please will use 4 pi 6 index card until I understand what it means. When we say Q is positive, that means the system is gaining heat. Let me just minimize that, and probably if this is the system right here, A plus B going to C, this is positive Q, and it is endothermic. This is endothermic endothermic reaction. That means by positive Q came by the system. If it is losing like that, going away, this is and by the way, this is less, no, greater than, it's greater than 0. Q negative, this is exothermic reaction. Exothermic reaction. And anything less than 0 is negative. So that is what is this for Q, which means where Q is heat, energy, is heat energy. For the W, which is work, it can also be work done by the system. This means plus W, and is greater than 0. Work done on the system, or negative W, which means less than 0. Work done on the system. For E, positive means net gain of energy by the system. We're talking about the energy means net loss by the system. We will, all right, we will perform calculation based on the statement you see on this slide, which means calculate the total internal energy. You need to wrap this around your mind. Is the system doing work? Is work being done on the system? Those are the things which will influence how you write, how you use this equation. Change in the internal energy is Q plus W. Both of them can be negative, both of them can be positive, one of them can be negative, and it will influence the overall value for change in internal energy, Probably maybe when I get to an example on calculation, you will see. But before that, I defined earlier on what endothermic is. It's a reaction which absorbs heat from the surrounding. For example, reaction between barium hydroxide octahydrate is anhydrated salt with ammonium, the ammonium cyanide. All right, it is an endothermic. You may not really see from where you are, but the temperature has dropped from 0.023 degrees Celsius to negative 0.11 degrees Celsius. It's endothermic. It's absorbing heat from the surrounding. Whereas exothermic means it keeps away heat. Dropping potassium or sodium in H2O is highly exothermic, and the temperature will go up if we were to measure the temperature for H2O. exothermic, endothermic. So the point here is you should be able to define exothermic, endothermic, or differentiate between endothermic and exothermic. When a system releases heat to the surroundings, say the reaction is exothermic, endothermic. I gave you earlier on the sign convention. I walk you through this. Please go over again. Remember Q. That's what I wanted to highlight. Q means heat or thermal energy. W means work done. And it can either be work done by the system, work done on the system. Please read more on that as well. Here is an example now on calculating the internal energy or just change in energy. As you see here, unless you know what this means, unless you know what the system means, you will not be in a position to move forward with problems such as the one you see on the PowerPoint slide. First of all, a system releases 225 kilojoules of heat and does 120 kilojoules of work on the surrounding. What is the change in internal energy? At the outset, all right, you just minimize this so that you can see the whiteboard. At the outset, internal energy, change in internal energy equals to Q plus W. But if you look here, a system, so if this is our system right here, A plus B going to C, like that, A plus B going to C, you're saying the system releases heat. That means it is getting out of the system, which means negative Q. And does work on the surroundings. So it's getting out, that means negative W. So if I am to fit in here, it's gonna be negative Q plus negative W. So in other words, if heat was absorbing, we will have this as positive getting in there. Sign convention. Work done. Look, does work. That means the system is doing work, is carrying out. So I'll have it as negative. How do I know that? It's based on what we talked about here. Work done by the system is going to be negative. System loses heat. So it's going to be, it's losing. So it's negative Q. I think probably maybe the other one is more elaborate. Let's see if I had it right. Yeah, right here. So means the system loses positive, negative. These are negative, by the way. It's not a bullet point, but negative means net loss. Negative means done by the system. And that's why I have negative here. I'm gonna have negative here. It was done by the system. It's losing, so it's gonna be negative Q. That's how I'm arriving at this setup right here. This is just general right here. This is general. If you don't pay attention to the sign convention here, you may think that this slide doesn't really matter. I know it's negative, but it will have an impact on how you set up your calculation, and you'll get confused when you are given multiple choice problem, and two values are the same, but one of them is positive, one of them is negative. Which one? For example, if somebody doesn't change the value here, you end up with something else. So for this, it will be negative 2225 kilojoules plus negative 120 kilojoules, negative 120 kilojoules. And what we'll get here is you just have to find the summation. All right, find the summation and see what the value will keep. This will be negative 345 kilojoules. This will be negative 340. Did I put too many twos? Yeah, sure. This is joules, by the way, not two. So I guess I need to write it correctly. This is negative 225. 225. Is it kilojoules? Yes, kilojoules. And this is 345 kilojoules in total. This is what I was saying that in multiple choice quiz or exam, this might be positive 345 kilojoules, negative 345 kilojoules. If you don't do your homework with the sign convention, you will get it wrong. Sometimes the problem could be work is being done on the system or the system is doing work. You need to know how to play your cards well. Please look at problem number 43, all right, 44 and 45. I believe for all problems, you have the solution at the back of the text. For more practice before you attempt module 7 Alex assignment. Now, this is how the system exchange energy with the surrounding. It can either be in form of heat, which is Q. We're going to be using Q to denote the heat and W to denote the work. This is the only way the system can exchange heat with the surrounding. It can be in form of work, can be in form of heat. So please just understand what I mean. There is a white period ball illustration in the text, you know, how the energy is transferred and how the energy is conserved. You can look more on that to show or to understand how the system or change in internal energy of the system equals to the negative. That means the surrounding is gaining, lost by the first ball, gained by the second ball. Illustration just by transfer of energy. Transfer of energy. If you look at how energy is transferred, it's total. Energy cannot be created or destroyed. The net change is far throughout. The same thing after the collision initially, some is lost on the way. Whatever remains will be transferred into the second ball, right? This now has a net kinetic energy of 0, whereas 2.0 joules and 3 joules are used to do work and at the same time transfers heat. So let's see for a conceptual question such as this, which heat exchange is best classified as work? An ice cube melts and cools the surrounding. Remember how I define work or how work is defined. It is force times distance. Force acting on an object over distance, all right? If you are holding on like 20 pounds stone and standing on the same position, you get tired, you're not doing any work because work equals to force times distance. So here I don't see the distance. A metal cylinder is rolling up the ramp. Yes, if you roll it up, there will be like some distance being covered. Steam condensers on the skin causing a burn. We don't have distance in this case. So A and C are wrong. The correct answer is B. I just want to see if you understand what work is, right? Metal cylinder is rolled up a ramp is an example of work. Work is force times distance. Force times distance. Lastly, for 7 or part A, 7.4, last section in part A, 7.4, quantifying heat and work. Quantifying heat and work. Do we quantify that? Heat is the exchange of thermal energy is because of the temperature, the surrounding, okay? It occurs when a system and surrounding have differences in temperature. Heat flow from, hot to cold, transfer of heat. We can measure the temperature, all right, which is a measure of thermal energy within a sample. It's just the average kinetic energy of atoms or molecule in an object. It's just the definition of a temperature. And this flow, the heat flow as a result of differences in temperature. High temperature, okay, the heat will flow from high temperature matter to low temperature until both reach what we call thermal equilibrium. They will all have same temperature. We say thermal equilibrium. There is no net transfer at that point. When they have two objects have the same temperature, we say they are at thermal equilibrium. We can quantify work using this equation, Q times the heat capacity, which is defined as the amount of heat required. Let me just define this. You need to define this, I know. So on the line, there will be some definition. I want to define this term right here. You will also see, you may see in the quiz or in the next exam. Heat capacity. This is simply amount of, heat required to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. It's the same thing, 1 degree Celsius or 1 Kelvin. We don't specify the amount of matter. This doesn't really matter. You may have 10 ml of H2O. If you can raise by 1 degree, it's the amount of it required. How much do you need to raise that is heat capacity. We use here units is joules per degree Celsius. You need to know that. Units for heat capacity. We designate that using uppercase C. It's the heat capacity. This means heat capacity. Whereas there is what we call specific heat capacity. I've seen some others just using the lowercase s. I may use SP, specific heat. That's the same thing for me. How do we define this? You need to be able to differentiate the heat capacity from the specific heat capacity. Specific heat capacity is amount of, look at how you define this, amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius by 1 degree Celsius. So that's how you define specific heat capacity of a substance. You'll see some of the literature values for some few substances in the text, you'll be given that these two terms we'll be using. So back to our heat capacity. Remember, the unit is joules per degrees or joules per Kelvin. It's the same thing. We designate using the uppercase C. Take note of that uppercase C. Here, the units for this is joules per gram times degrees Celsius. This is the unit for specific heat, which is different from the units for the joule. Sometimes I see multiple choice question, what are the units for heat capacity? What are the units for specific heat capacity? How do you define the specific heat capacity? How do you define the heat capacity and so forth? So we can calculate Q, which is the heat, using two equations. You need to remember this heat. Q can be or determined, all right, can be determined using these two equations. There are two equations. One, depending on what you are given, it could be Q equals to C, which is the specific heat times the change in temperature. Whereas this is the heat capacity, and this is the change in what? Change in temperature, change in temperature. All right, change in temperature is T final, all right, T final minus T initial, the initial. T final minus T initial. You see T final minus T initial. You're going to be reading problems. The temperature changes from 24 to 26. If you have to calculate, change in temperature is final minus initial. Remember, this means change in temperature, change in temperature. That's what that means. So we can use this equation or rather here to Q equals to M times specific heat times change in temperature. Sometimes it can be M times PS times change in temperature, where M mass in gram, CS is specific heat, and this is a change in what? Change in temperature, change in temperature. Change in temperature. So remember, there are two equations for calculating the heat. This is the heat, right? Either the first equation, if you are given the specific, all right, specific heat capacity of a substance, or if you are given the heat capacity of a substance, change is the same as just final minus initial. Now, the heat capacity, the larger the heat capacity the object being studied, the smaller the change in temperature before for a given amount of heat, for a given amount of heat. These are just, factors affecting the heat capacity. It depends on the material, it depends on the amount. It is an extensive property. Remember how we define extensive, intensive property? So that means the more we have, the more the heat capacity of an object will increase in temperature. Here, let me just blow up this, show you a few substances in the text with their given specific heat. This is different from the heat capacity. Remember how I defined the heat capacity? Specific heat capacity, it is an intrinsic ability of a substance to absorb heat. And it's defined. I defined that for you. It's the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. If need be, you will be given this. If not, if let's say you are attempting end of chapter problems, you may need to refer to this table for specific heat capacity of few compounds given here. Take note of the heat capacity for H2O. It is the highest if you look at this, and this explains why, let's say in Bay Area in California, during summertime, about like 2 miles inland in Bay Area, it is extremely hot. The temperature could be in hundreds. But when you get to the Bay Area closer to the water, the temperature is cool, around 68. Why? It's because of the high specific heat capacity of H2O. That's why people love to go to the beach. It's cool. I know maybe some people go to the beach for other reasons, but main reason is you unwind and at the same time enjoy the cool breeze coming off the ocean because of the high specific heat for H2O. I have defined this. Please be able to define that as well. Note the units. Look at the symbol for specific heat. There is C and then S. I guess S for specific. For heat capacity, there is no S. It's just uppercase C. You should know what it means. Likewise, for the units, it's joules per gram times degrees Celsius. The other one was just joules per degrees Celsius. That, so that when you plug in, you'll get that. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance. All right, by 1 degree Celsius, 1 mole of a substance by 1 degree Celsius. You may also need to define that. I just gave you an explanation as to why it is cool in Bay Area. This looks like Golden Gate Bridge in California, been there once. It's just to show that why it's cool. You see, there is it's foggy, making it cool during summertime. The large amount of water absorbing the heat from the air keeps the beaches cool in summertime. This is why some of you may be frequenting, or maybe you just love hanging out by the beaches because it's cool because of the specific heat. Just remember to tell your friends and remind them that you learned in chemistry class why it is cool by the beach. It's because of what? Because of high specific heat for H2O. This is a San Francisco illustration. Look at this. Inland. Sacramento, which is inland, and San Francisco may be as high as, this is the difference, about 20 degrees. Yeah, wow, that's light, right? So in our specific heat, let's say, suppose you are cold weather camber and you decide to heat some object to bring into your sleeping bag for added warmth. You place a large water jug and a rock of equal mass near the fire. Over time, both the rock and the water jug warm to about 38 degrees Celsius. If you can bring only one into your sleeping bag, which one should you choose to keep your warm? Is it the rock? Is it the water? Is it the rock because is it the water because it will absorb more heat as it cools? Or is it because water it releases more heat as it cools? You want the one which releases, right? So it's gonna be A. This has to do with the specific heat we just mentioned about that. Please read more on the specific heat. There is a paragraph or a page on this conceptual question, the specific heat for H2O, specific heat for H2O. So you can quantify, or we can quantify heat using the mass, a specific heat. This is the equation I gave you earlier on. And the units will be in joules. By the way, you have to be careful because sometimes you may be asked to quantify heat in kilojoules. So that means you're going to use this equation. Once you have your value in joules, you change to kilojoules. 1 kilojoules equals to 1,000 joules. So this is the change in temperature, which is final minus initial. CS, this means specific heat. And remember the unit so that when you cancel, you'll end up with the joules, Please, this is how the units end up with that. So that if you have mass, Q equals to mass in grams times joules in grams times degrees Celsius times degrees Celsius. So that when you look at this, cancel that and that, cancel this and this, you'll remain with joules. So that's why this will be joules. If you have to change to kilojoules, remember 1,000 joules equals to 1 kilojoules. This is just an equivalent statement. You don't need it, but just remember if you have to convert to kilojoules. Let's see. This is an example on, all right, quantifying heat. An example on quantifying heat. A 55.0 grams of aluminum block initially at 27.5 degrees Celsius absorbs 725 joules of heat. What is the final temperature of aluminum? Of course, there's some missing information here, which you cannot, unless otherwise you have memorized. You need to remember that Q equals to mass in grams times CS, which is the specific heat in joules per grams times degrees. This is for aluminum, Al times change in temperature, which is T final minus T initial, T final minus T initial. All right, T final minus T initial. If I look at this, if I number this as 1, 2, 3, and 4, if we know 3, we can calculate the 4th one. So we are looking at the T final, we know the initial. This is missing. We know that, we know this, we know that, we know that, we have those. So you have to plug in the equation. In this case, I don't have, we don't have the the specific heat of aluminum, we need to refer to the relevant section to have the specific heat of aluminum. All right. How do you know that? You don't need to worry. I'll give you in the exam. Let me just go back to the section. This is where I want to. You see aluminum? This is the specific heat. You'll be given for a problem unless you are asked to calculate the specific heat. You'll be given all the information for you need for that. So once I write down that, or if I'm given that, all I have to do is now just write down, take note the specific heat. I'm going to minimize this. You see my whiteboard. So CS for aluminum is 0.903, 0.0. And this is used per grams times degrees Celsius. Can I have that? You're gonna have that. So if we plug in the equation, it will be 7. This will be 725 joules equals to mass, 3 significant figures. So our final answer will have 3 significant figures times 0.903 joules per grams times degrees Celsius times now T. We're looking for final, T final minus initial, which is 27.5 degrees Celsius. So if we crunch the numbers, this will be 725, all right? Uh, 725 equals to, let me multiply that. This will be 55 times 0.903. I have 49.665 into T final minus 27.5. So if I divide both sides by 49.665 over 49.665, I'll remain with T final minus 27.5 equals to, so 725, I'm just gonna divide that, 725 divided by 49.665. This will give me 14.5978. But taking this across the equal sign, all right, it will change to positive. So here will be plus 27.5 plus 27.5. So T final, T temperature final equals to 42.0978, which is more than what we need for our significant figures. This is 42.1 degrees Celsius, 42.1 degrees Celsius. So this is the what? This is the final, temperature. That's the final temperature. I need you to practice with problem 48, 49. I believe you have the answer. The back of the text. Problem 50 on page 3 or 7. More practice also you will come across in module 7 for in Alex on quantifying heat. Feel free to use the table. If you are not given the specific heat, please use the table to find the specific heat, just the way I did for aluminum. I'm not given here, but in the exam, you'll be given the specific heat for substances if need be. Well, let's see, thermal transfer. We talked about this heat being lost by one substance is gained by another substance as a result of heat transfer from hot objects to cold objects. The amount of heat energy lost by hot materials equals to the amount of heat gained by the materials. So here, the Q system, this means the heat of the system. If it is exothermic, the surrounding will gain. You see, if our object is, or the system is a metal block or metal slug, at a higher temperature is placed in water, the system will lose heat, whereas the surrounding will gain. System equals to the negative. It's gaining the heat based on what we have, the transfer. For example, a plug of metal at 55 degrees is submerged in water at initially 25. We can calculate the amount gained or loss of the amount of thermal energy transfer. The exact temperature change depends on the following: the mass of the metal may be given for that, the mass of H2O, and the specific heat capacities of the metal and H2O. You will see that when we have the metal minus H2O. So if you are to determine the thermal energy transfer from metal to H2O, this is the equation you will need. You'll refer to the specific heat of water, the mass of H2O, you have a change in temperature. Remember, the final temperature for both will be the same. At the end of it all, they will reach thermal equilibrium. So T final for both of them will be the same, but the T initial, that is the initial temperature, will be different in this case. Let's see a problem on thermal transfer. That means heat is being transferred from a hot object to a cold object. When they come in contact to reach thermal equilibrium, that means they'll have the same temperature. Remember, the equation we'll be using is this one right here. The metal, everything will be the same. We set up this way, we set up that too as well. So how are we going to find what? What are we looking for in this problem? A block of copper of unknown mass has an initial temperature of 64.5 degrees Celsius. So 3 significant figures at the end because of the first value we look at here. The copper is a mass. That means it's going to be dropped in a beaker containing 95.7 grams of H2O at 22.7 degrees Celsius. So remember, this is the T initial for the plug of copper, which is hot now. And this is the T initial for what? For H2O, which is cold. They will reach a final temperature. The T final will be the same for both of them. When the two substances, that means the plug of copper and H2O, reaches thermal equilibrium, the final temperature is 24. What is the mass of copper? So we need to find the mass of copper. How are we going to find the mass of copper? We'll have just to say here, we just minimize this right here. We say Q for the copper, negative Q for what? Which is mass of copper times specific heat, or maybe I should use CS for specific heat of copper times change in temperature equals to negative mass of water times CS for copper times change in temperature. So what we are looking for is the mass of copper. Is the mass of copper. Clearly, we are not given the specific heat for this problem. You need to find out the specific heat for copper. CS copper is 0. This is given in the manual on the table. And remember, it's joules per degree Celsius. CS for water is 4.18 for joules per degrees Celsius. These are, and this is grams, by the way, grams. Specific heat, you need to have those so that you plug in this equation right here. This is the equation for thermal transfer. You need to remember that it should be a negative. So if we plug in that, this will be the mass of copper times 0. Or I'll just have to times 0.8 joules per gram times change in temperature, which is 24. This is the final 2 minus 65.4 equals to, on the other side, mass of H2O is 95.7 grams of H2O times 4.184 joules per grams times degree Celsius times 24.2 minus 22.7. This will be minus 15.862.7 m, which is the mass, equals 600.039. Mass equals to 37.8 grams. So this is the mass. Find in the calculation, this will be the mass. So pack up a little bit. This is the equation you need to use. You have to think of thermal transfer using these two equations. That means quantifying the heat for copper and the water loss. Remember, one is gaining, one is losing. Specific heat, if not given, you have to refer. For example, here, we were not given the specific heat for both substances. I had to look up from that table. The table I was using earlier on to get these values. So even for you, when you look at those problems, I'll come back here. Look at this. specific heat. This is where I got the values. All right, this is where I got the specific heat for copper, specific heat for H2O1, 4.18 or 4.184. So remember that. If you are not given, feel free to refer to that table and use the equation for the transfer. This is how you set up your calculation for thermal transfer. How do you know that this is a thermal energy transfer problem? If the question is stating that a hot object was dropped in a cold substance and both of them came to a thermal equilibrium, there is thermal transfer, and this is the equation. You will need to do that. You need to use that. Please look at problem 69, 71, 73 on page 308. It is relevant to what we just looked at. Use the same approach as the calculation I use here. And this is the mass of the copper block we use in this problem. Copper block used in this problem. So now let's see quantifying work, or rather pressure volume work. Sometimes we call this PV work. When system expand, they do work on the surrounding. If I'm holding on to, let's say this is a calculator. Visible is a calculator, you can see. If this is a calculator I'm holding on, assuming that it is a tube for a bicycle and I'm putting pressure in there, it will expand, it will expand, expand. It will do work on, in this case, the tube, be it for bicycle, or it will do work on my hand by expansion. So when a system expands, it does work on the surrounding. Or if it contracts, that means the system or the surrounding rather is doing work on the system. We are moving on to PV work. We just have that and have it here as PV work, like that, PV work. Just title that as PV work. When it's expanding, change in, gonna be using this as well. This means change in volume, which is V final minus V initial. So if you look at this diagram right here, cast and close right here, it will expand. Look at the piston. It will be pushed against external pressure. Therefore, system does work. So work, this is the equation for work. P, again, is the negative here means against external pressure. There is a negative here. Please look at my cursor, negative. And then change in volume, which is V final minus V initial. V final minus V initial. Oh, sorry, I just didn't have my whiteboard. This is the equation for calculating work, W for work. And again, go back to work done by the system, work done on the system. Note, all right, note pressure must be, must be in ATM atmospheres. Remember in chapter 6, gases, atmospheres. You have to change to atmospheres using appropriate conversion factor. If it is in torrs, PSI, anything else, you have to change the pressure to atmospheres. That is one. Two, volume must be in liters. Must be in liters. Because, why do we have to do that? We want to relate to energy. 1 liter times atmosphere equals to 1 or 1.3 joules. This is an equivalent statement you will need. I'll give you in the exam and give you in the quiz, so that you use in, all right, you use to convert whatever you will get into the joules, into the right units. Remember, in this equation, pressure has to be in, look at, pressure has to be in liters, pressure volume has to be in liters. So the unit will be liters times atmosphere, which means 1 liter equals, this is an equivalent statement you'll use to change to express the energy or the work done by the system or on the system using the appropriate units, joules, which is what? Which is the SI unit for work. Let's look at this. PV work is pressure volume work. PV means pressure volume work is caused by volume change against external pressure. There is an external pressure here. When a gas expands, change in volume is positive because final is always higher than the initial. Therefore, the system is doing work on the surrounding. Please be very vigilant. Commit to your memory these terms. When we say work is done by the system, when it's done on the system, it will affect the sign convention for your PV work, or how you set up your calculation. It will impact your final answer in terms of signs as well. As long as the external pressure, all right, is kept constant, this is the equation for calculating the work done. To convert that, this is what I gave you. You need to remember that, okay? So if this is expansion, final, okay, minus initial give you change in volume. Maybe solving a problem will help you out. Let's see, learning problem here. If I'm to, all right, solve this problem using the equation work equals, remember, a cylinder with a piston expands from a volume of 1.003 significant figures to 2 liters against an external pressure amount. How much work in joules? If it was in kilojoules, then we'll convert that, but it's in joules. So what is PV that is changing? Always the negative here is because against, when we say against external pressure, against, that means negative right here against that. So here, negative PV into V final minus V initial. This will be 1.00 ATM times 2.00 minus 1.00 liters. So 2 minus 1 is 1. So it turns out that this will be 1.00 liters times atmosphere. This is the unit because this will be in liters, this is in liters, this is the atmosphere. That's what I do have here. But This is not a final answer. We need to express our answer in joules. So, using the conversion factor, times you have to generate, you want to get rid of liters times atmosphere. Remember, 1 liter times atmosphere, ATM equals to 101.3 joules. This is what we'll plug in here, 101.3 joules. This is one right here. Liter and liter will go, atmospheres and atmospheres will go, and this will be, there was a negative here. So the correct answer is 101 joules. I know you may have 101.3, but because here we have 3 significant figures, we'll just ignore the 3 here. Is less than that. The correct answer is D, as in David. The correct answer is in D. Please remember how to keep track, change the pressure to atmospheres. Volume should always be in liters. If not, please, you need to change to liters. You need to change to liters. That's how you find that. Or likewise, let's see one more problem here. Calculate the work in joules if the volume of a system contract. This time is contract, all right? When say contract, final is always less than the initial. So solution for this is, it's gonna have a solution. Work equals minus the change in volume where change in volume is given by 0.85 liters minus 1.55 liters. It's gonna be negative 0. What? The volume for that will be negative 0.70 liters, negative. Right? So this will be negative. External pressure here is 0.985 atm times, maybe I need to erase here and say this will be now negative 0.985 atmospheres times negative 0.70 liters. This will be on the calculator, it will be positive 0.6895. All right, with your calculator, 5, and this is liters times atmosphere. This is not the correct unit, the correct form. We need to change to joules. Remember, here is in joules. So this will be, therefore, in joules, this will be 0.6858 9 5 liters times atmospheres times, now the conversion factor is for every 103 joules 1. All right, 1 liter times atmosphere. So that atmosphere and atmosphere equal, liter and liter equal. This will be 69.8 joules, 69.8 joules. the point here is please always remember to use the conversion factor here. This is conversion. Conversion factor for that. All right. This is the conversion factor for that. So it's positive, the change in negative times negative. Remember here, this will be negative, so there is a negative and there is a negative, it will be positive. It will be positive. So take care of contraction if the system is contracted. I want you to also look at problem 53, 55, 57, 58 on page 307. It's going to help you in more practice before you complete the Alex assignment, module 7 on PV work. This marks the end of part A. Please.